Hey everybody, Chris McClure here. We're going to now hit the material in section 4.2 where we are looking at fitting linear functions to data provided that the data are somewhat linear in nature. So that's what we're going to talk about in this section. So we're going to first take a look at determining whether there is a linear relationship between two variables by looking at a scatter diagram. So suppose that you go out and get several pairs of data. Now what I'm talking about you have two variables, height versus weight, humidity versus temperature, whatever, and you make several different readings where for each reading you collect both a value for the one variable and a corresponding value for the other variable. So for example, in this example here, throughout the course of a day in a room at these different humidity levels, and by the way, we have X as the variable for humidity. So for each of these different relative humidities, we have these apparent temperatures, Y variables, Y values. So when it's 10 degrees humidity, so 10% humidity relative, I should say, that corresponds to 65 degrees apparent temperature. Now, when I was down there in South Carolina last week and week before, it was closer to about 90% humidity. And at 72 degrees Fahrenheit outside, that translates to an apparent temperature of 75 degrees. Anyway, so you've got a whole bunch of ordered pairs. And of course, here are the different ordered pairs, written as ordered pairs. So now we're looking to see what is the relationship between relative humidity, which we are pegging as our X variable, and apparent temperature in degrees Fahrenheit, which we have as our Y variable. So we go through, and on XY axis, we're going to plot all these ordered pairs. So, in other words, we're going to create a scatter diagram. So here's what that scatter diagram looks like. You know, if we create it by hand or using a computer, this is what it would look like. And these little symbols right here means page break. We're going to not let the graph go from 0 to 62 all the way down here. That'd be a lot of dead space. So we just say we're going to go quickly from 0 to 62 just by introducing this little page break. On the horizontal, we've got relative humidity from 0 to 100%. On the vertical, we've got apparent temperature in degrees Fahrenheit. And you notice that we've got these dots. These dots are the plots of those ordered pairs from the previous slide. This is what it would look like if you were to plot this on your graphing calculator. And give me just a second. I'm going to show you how to do this on your own graphing calculator. Okay, so pull out your graphing calculator. And I'll pull out mine here in just a minute. And I am going to show you how to input this data in your graphing calculator. Now, see where it says stats right here on your graphing calculator? Go ahead and click stats. Now notice that there are three different submenus. Well, let's select the edit submenu and the first option on the edit submenu. And notice that we've got three different lists, L1, L2, L3. In fact, lots of different lists. that you can use. But we're going to edit list L1 and L2. Let's clear all this stuff out of here. You may be empty or not, but I'll show you how to clear this list just by up arrowing into the column header and pressing the clear button. Then down arrow. Do that again for L2. Up arrow, clear, down arrow. Now let's go ahead and input all those data pairs, starting off with the X values, which are the humidity values. Starting off at 0, enter, and then 10, enter, and just go on down the line, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then right arrow over to L2 and then input those corresponding apparent temperatures. So the first one is 64, then 65, enter, 67, 68, enter, 70, 71, 72, 73, 74, 75, and finally 76. Okay, now that we've edited lists L1 and L2, let's go ahead and quit out of there. And then you see up here where you have your equation editor, y equals button, and notice up here it says stat plot. So to access that menu, the stat plot menu, hit second and then the equation editor menu to go into your stat plot. Now let's go ahead and choose option 1. You could choose any of these stat plots, but let's go ahead and choose stat plot number 1. And let's go ahead and turn it on by highlighting the on option and entering it. And then we're going to down arrow to type, and let's highlight this one right here and then select enter to select that. Now your X list is going to be L1, and if you need to change that list L1 for X list, then go hit second and list right here, and then choose list L1 right there. And likewise, make sure that this Y list is L2. And then finally, you could choose whatever mark you wish down here. But I'm just going to choose that big fat one right there. Now, let's just go ahead and quit that and go into your menu, your window, and let X minimum be, say, -10. Sorry, -10, not -10, but -10. Enter. X maximum, let that be 100. Actually, 110. How's that? Enter. X scale, let that go by tens. Enter. Y minimum. Let's go from, say, 60 to, say, we meant to do 60 there. Let's go 80 for the Y maximum. Maybe by 20s. Actually by 2s, sorry. Okay, by 2s. And then, by the way, go back in your equation editor here and clear out that function if you got a function in there. Clear that out. Then go ahead and hit graph. And there you see the stat plot, aka scatter plot, for those data pairs on your graphing calculator. And you can see that there is a highly linear relationship between the relative humidity and the apparent temperature. Alright, so that kind of... This picture here is very similar to what we had. Maybe they use different values for it. Well, their Ymin and Ymax is different from ours, but otherwise it's the same. Okay, so we could see that as relative humidity increases, that corresponds to a direct increase in the apparent temperature in a linear fashion. Alright, so we see that if there is a somewhat linear arrangement of those dots in the scatter plot, that means that there is a linear relationship between the two variables. So we could have this positive linear relationship, or in the negative sense as well, if you have a positive or negative slope for the equations that would model that relationship. But these two right here are examples of scatter plots that show a non-linear relationship. Maybe this one for part C shows a quadratic relationship between the two variables, or maybe this one here for part D shows a cubic relationship between the two variables, but they're certainly not linear relationships. Maybe this is an exponential relationship here, but again, not linear. So is this one linear? Yes, it is. It's linear with a negative slope. What about this one? And the answer, of course, is this one right here is nonlinear. Okay? How about this one for part C? You'd be right if you said nonlinear. What about this one right here for part D? And again, it's nonlinear. That's more exponential in nature. So how can we come up with a mathematical model to show that relationship? A mathematical model? Well, one thing that we could do is just pick 2 points in the data set. Like, for example, from that previous example, maybe we can pick this point here, 10,65 and 80,74. And then use those as 2 points then to come up with an equation, which we know how to do. So we can calculate the slope, like we know how to do. Rise over run, right? 70 minus 65, sorry, 74 minus 65, I should say, divided by 80 minus 10. So that's 9 over 70 would be the slope. Then choose either one of the points for your point slope form. There's your point slope form. And so choose one of the 2 points that you use to calculate the slope, either this one here or this one here, and plug in the y-coordinate for that point there, and plug in the x-coordinate right there. And it looks like we're using this point right up here. So you plug in 65 there for y1 and 10 for x1. And of course the slope goes right there. And then multiply, simplify, collect like terms, and so forth. And boom, this equation right here would be a model, a mathematical model for that relationship between relative humidity and apparent temperature. So if we then were to plot that line, this line right here, on top of the scatter plot, then that's what we would have. So let me go ahead and write that equation down. So we have 9/70 x plus 4/46. And then let's go over to the graphing calculator and go into our equation editor and plug in, and let's use parentheses here, 9/70 x plus 4/46 plus 4/46. Enter. And as you could see, when we graph, that line goes right through those points on our scatter plot. And we can see that that equation that we came up with is a pretty good approximation. It kind of fits that data. So it's a suitable mathematical model for us. Okay, so now let me show you how you can use your graphing calculator to come up with the best line. Because that line we just came up with is a pretty good line, but it's not the best line. We're going to come up with a line of best fit, what we call a least squares line. And for those of you going to be studying statistics anytime soon, you'll learn more about this regression line or least squares line, what they're calling a line of best fit in this textbook. So I'm going to show you how to use your calculator to come up with the equation of your regression line. So now let's go back into your graphing calculator. There's our graphing calculator right there. Graphing calculator, go back into your equation editor and clear out that function. It was a good function for us, mind you, but we're going to come up with a better one. Let's quit out of there. Now, I'll show you how to get your equation of best fit, your line of best fit, regression line, least squares line, whatever you want to call it. All right, go into your statistics menu, go over to calculate, right arrow, and then go down to option 4, where it says linear regression, AX plus B. And then hit enter. Now, if you don't see this R and R squared down here, don't worry about it. We're really not talking about that, at least for now, right now. All you need to focus is on the A and the B. The A is your slope, as in right there, that A. And the B is the y-intercept. So your equation now is going to be y equals 0.121x plus 64.409 approximately. You can kind of truncate these 2 decimals to maybe 2 or 3 decimal places, and you'll have a pretty good approximation. Okay, so that's what you see there. We just did that right here. Again, don't worry about it if your graphing calculator does not display the R squared or the R. Those two refer to how well the line fits your data. So we're not having that discussion today, though. So now let's graph that line of best fit. So go back to your equation. I'm going to show you something real interesting. Go and redo your linear regression. But before you hit enter, I'm going to show you how the calculator can paste your regression equation right into your equation editor by going to your variables menu and then right arrow over to the Y variables menu. Select option 1 for your function and then select whichever Y suits you, like Y1 or Y2. Let's select Y1. So what's going to happen, the graphing calculator is going to come up with your regression line and paste that equation in your equation editor. Now, notice that there's nothing in there right now. Now we're going to go ahead and hit enter on the home menu here. And you see the linear regression equation right here with the slope and the y-intercept right here. Now go into your equation editor and notice that the big long, with all the decimal places, this linear regression equation is in here. And then you graph it, and that line goes right through all those points. In fact, if you squint and look really hard, you could see that does even better than that previous one. So this line is the line of best fit, linear regression line, least squares line. Interpret the slope. What was the slope? Remember, we had this discussion before. The slope of your linear function is the change in y over the change in x. What was y in this case? Y was the apparent temperature, and x was the humidity. And the slope is 0.1209 approximately. So you can interpret the slope of 0.1209 to say that the apparent temperature increases by 0.1209 degrees for every 1% increase in relative humidity. Okay? Use the line of best fit to predict the apparent temperature when actual temperature is 72 degrees Fahrenheit and relative humidity is 45 degrees. Okay, well, this data was for 72 degrees Fahrenheit. So, in the relative humidity, that's the x variable. So when x is equal to 45, what is the predicted apparent temperature? Let's go back to our equation, into our graphing calculator here. Let's go onto our table here. Go into table set. We could start off at 0, and maybe delta table would be 5. Enter. Now go into table. Go into table. And so as we scroll down through these different relative humidities, we can get down to 45. Aha. So when the relative humidity is 45%, we see that there's a corresponding apparent temperature of about 69.85 degrees. So that would be our answer. Okay. Otherwise, you could take that equation, take 45 for x, multiply by 0.1209, and then add 64.409 approximately, and then round that to about 69.8 degrees Fahrenheit. So basically, when the apparent, or when the relative humidity is about 45 degrees, and the temperature outside 72 degrees Fahrenheit, that means that the apparent temperature would be 69.8% Fahrenheit. Okay? Alright, so that's it. It's basically a matter of doing linear regression if you have reason to believe that there is a linear relationship between two variables. Well, how would you know that? Well, you do a scatter plot with the data. And if that data is roughly linear in nature, then go ahead and do linear regression to get your regression equation. All right. Later on, we'll be looking at doing regression with other sorts of functions like quadratic or cubic or logarithmic, that sort of stuff. Okay, so that's it for today. Have a happy 4th of July. I'm not going to record anything tomorrow. And tomorrow would be July 4th. But I do plan to record section 4.3 material on Friday. So look for it. But hey, if I don't get around to it, have a good weekend anyway. And we'll see you later. Take care.